Question 4. So there is one halogenous alkane exists as a pair of stereoisomers. Part A. Draw the 3D structure of the two stereoisomers of this halogenous alkane. R can be used to represent this alkyl group. It's okay. So first, when you see this dotted line, vertical dotted line, so this is actually something like a mirror. So you need to draw the optical isomer. First, you need to find out or identify the chiral carbon. So the chiral carbon is this carbon, this one. And you need to get the 4 different groups that bonded to this carbon, which is the bromine, the methyl group, and this alkyl group, and the hydrogen. So there are 4 different groups bonded to the chiral carbon. And for the 3D structure, you need to draw the wedge line and the dotted line. The wedge line is the one that more near to us, right? So it's in front. The dotted line is at the back. So means when you try to draw the 3D, just remember to draw these 2 lines. You can put the 4 groups randomly, means in any order is okay. Once you put in the certain order, like the one that's shown on left hand side, then the mirror image you must draw the compatible one, right? So let's start with this one. Okay, the left hand side, this optical isomer. So once we complete this one, okay, the carbon with bromine, hydrogen, methyl, and this alkyl, then we need to draw the mirror image. Okay, put the carbon, okay, the hydrogens on this side, bromine on this side, and the methyl group must point to this one, right, at the back, and this alkyl group is in front. So if let's say you want to, for this drawing, you want to put CH3 like this also can, no problem. It depends. Now this is the mirror images that you need to draw. Part B, a sample of this halogenous alkane reacts with the sodium hydroxide to make this alcohol in the SN1 mechanism. It's already given SN1. Then when you draw the mechanism, or when you want to show the mechanism, you must follow this SN1 mechanism. Means the first step, which is the rate determining step, it must involve one species only, right? So you must include all the charge, dipole, lone pair of electrons, and all the carrier arrows. Okay, so first you must, because it's SN1, so we must involve the halogenous alkanes only without hydroxide. Of course, the first step you need to do is to put the dipoles, because the bromine is more electronegative than carbon. So we put the partial negative on the bromine, partial positive on carbon. And you need to draw one arrow from the CBr bond, from this CBr bond point to the bromine. It shows that the pair of electrons here now is moved to the bromine, and it will form bromides later, right? So it will form bromides here. Bromide is not important here, it's okay. After that, it will form this intermediate, this carbocation. So because the CBr bond break and the carbon now is electron deficient, so it's charge positive. So to draw this carbocation, 1 mark. And you need to draw the hydroxide, because it's the hydroxide now donates electrons to the carbocation. So you must put a lone pair, only one lone pair on the oxygen, and draw one arrow from the lone pair point to this carbocation, to show that a new bonds form. The CO bonds will form, right? So eventually it will form this alcohol. So this is the mechanisms that you need to show, the SN1 mechanism. Part C. Separate samples of these three compounds, right? So this is halogenous alkane, alcohol, and this one you need to be careful. So this is actually alkene. There is a double bond here. Complete table 4.1. If no reaction, just put cross. Now let's start from the first one, the bromine in the dark. Okay, bromine liquid in dark. Observation with the halogenous alkane here. If bromine with sunlight or UV, then there is a free radical substitutions there. Because it say that in dark, so the free radical substitution is not happening. So you just put a cross here. Nothing happened for this part. This one no need to bother. Okay, this one. Observation with this alkene. Again, you need to know this compound is actually like this. There is a double bond here. CC double bond. So means bromines will add into this alkene, and means additions reactions happen. So means the orange color will decolorize. So orange to colorless. Okay, because the bromines added to the CC double bond or the alkenes there. For the PCl5, now PCl5 solid. Okay, observation with the alcohol. This alcohol, you need to recall what you learned in this reaction. When there is alcohol with PCl5, so the chlorine, one of the chlorine in the PCl5 will substitute the OH in the alcohol, and it will form this halogenous alkane. And of course, another chlorine will form the HCl here. Okay, it will react with the H here, right, to form HCl. The O will get into the PCl3 and form the POCl3. This is a general reactions that you must know. Means what you will see now is the HCl. When we put the PCl5 with the alcohol, because there is a OH group here, so therefore it will react in this way and it will form HCl. That's why you see steamy fumes. For the CC double bond, means this compound, observation with this, it will not really react. You just put cross here. For the silver nitrate solution, when this one's used together with the halogenous alkane, first you need to know, because it's aqueous, this halogenous alkane, somehow it will undergo hydrolysis, and this bromine will release as bromide, and it will of course form a cream precipitate with the silver ion. It will form silver bromide. So that's why you see cream precipitate, or nowadays you can say that it's off-white precipitate. Both acceptable. Observation with the alcohol, silver nitrate will not really react with this. Just put a cross here. Part D. The halogenous alkane is heated with D to produce three different molecules, E, F, G. The E and F actually they are the cis-trans isomer, the CC double bond here, the two larger group on different side, so it's a trans isomer. And for this one, the two larger group now same side, so it's a cis isomer. So and the G is another molecules or isomers that produced. Now name the type of reactions. First you need to compare with the reactants, the halogenal alkane. The halogenal alkane is look like this. So means the bromines will removed and the hydrogens on the adjacent carbon also will removed. So means this one there are two hydrogens here, and of course here there will be three hydrogens. So one of the hydrogens will remove and it will form this EFG. So obviously this is elimination because the hydrogens and bromines eliminated, right? So this is the type of reaction is elimination. Identify D and the condition needed. Because this is halogenal alkane, halogenal alkane form alkene. So means it must be sodium hydroxide in ethanol. So the conditions needed is ethanol. If water means it's substitution. When the sodium hydroxide in ethanol, so it's undergo elimination. So you must put sodium hydroxide in ethanol. Part E1. Both sigma and pi bonds are represented in molecule of E as a result of different types of hybridization in the carbon. Complete 4.2, table 4.2 to show the numbers of carbon with each type of hybridization in the E. So let's focus in this molecule. Just let you know the shortcut. Whenever you see the CC double bond, means this carbon with the double bond, right? These two. So it must be the sp2 carbon. sp2 carbon. When you see the carbon with all sigma bonds, no double bond, so it's all these carbon, they are sp3 carbon. That's how you remember, right? So therefore, sp hybridized is not going to be, because sp hybridized carbon, it must be triple bond, cc triple bond. So therefore 0 carbon, sp2 hybridized carbon, there are 2 carbon here. sp3 hybridized, there are 1, 2, 3, 4, 5, 6 carbon. Part 2. Describe the essential features of an unbranched hydrocarbon that causes its molecules to show stereoisomerism. Explain how this feature leads to the stereoisomerism. If it's unbranched, most likely it must depends on the CC double bond, like this, like the E and F. As you can see here, the trans and the cis isomer here. Because this one is unbranched, and the stereoisomerism means it's a cis and trans isomerism, is because of the CC double bond, right? So we need to use the CC double bond to explain this now. Okay, so first you need to, of course, say that there must be a CC double bond present in the molecule. This is the essential feature, right? And explain how this CC double bond will give the stereoisomerism. Okay, so after you mention CC double bond here, then there will be 1 pi bond and 1 sigma bond in the CC double bond, and this double bond will limit the rotation of the CC double bond. Means there is no free rotation happen, and it will fix the positions as you can see here. Means because of the CC double bond here, this one and this one, the bonding, it cannot be rotated, and this group now is fixed, it cannot move. When there is no free rotation and the position is being fixed, is always trans now for this molecule. And because of this cis double bond now is fixed, cannot rotate, these two groups also fixed at the same side, so it's cis. That's the meaning, right? No free rotation because these cis double bonds lock the position now. Okay, I hope you understand what I say, and that's all. Thank you.